the summation is just saying it's a collection of terms. What is this up here? It's a summation, right? We could rewrite this thing as a summation. So we could put a sum up here on the line, okay? We could rewrite this to look something like these other ones using a summation formula, okay? And so we're going to spend time talking about Bezier, and with that, we're going to come back and visit the other ones at the end, but we're not going to go into depth on them. So here's our Bezier curve. PU equals the summation of I equals 0 to n. N is what? Is it the number of points or is it the order? Well, because we're starting at 0, it's going to be the order. Okay? If we started I at 1, then it would end up being the number of points, but it's the order. So n is the order of the curve. Okay? P is just a collection of points that are used to define the curve or control the curve. And the B is the blending functions. What were the blending functions for the line? 1 minus u and u were the blending functions. So this B here are the blending functions, okay, for this curve. The blending functions actually have two parts to them. They're referred to as the Bernstein polynomial. It has this C n choose I, u I, 1 minus u to the I minus, to the n minus I. So that's the Bernstein polynomial. What does the n choose I mean? Well, it's just n factorial over I factorial times n minus I factorial. Just that. Something you'll memorize and learn the rest of your life. It's just that. So we have a series of points, 4 of them. We want to define a Bezier curve that works with these 4 points, and the Bezier curve is controlled by what is referred to as a control curve. Okay? And the control curve is a linear, it's a linear connection of these points, and the curve would look something like that. So let's talk a little bit about the behavior of this curve. P0 and P1 define the slope at P0. P2 and P3 define the slope at P3. The curve interpolates P0 and P3, but it does not interpolate the other 2 points. It does not go through them. Okay? So a Bezier curve is always controlled by its endpoints and by the beginning and ending slope, as defined by the vectors defined by P0, P1, and P2, P3. So if this is the example that we're going to use, we're using 4 points. We know what n is. What is n? N is going to be 3. Okay, it's 1 less than the number of points. Okay. And so we can begin to say, let's figure this out. Those are our 4 points. We need to start with the n choose I. And so for the first one, it's C3, n is 3, comma 0. If we put those values in, n factorial, which is 3 factorial, over I, which is 0 factorial, 3 minus 0 factorial, ends up being 1. For the 3 choose 1, 3 factorial over 1 factorial, 3 minus 1 factorial, it ends up being 3. 3 choose 2 is 3, and 3 choose 3 is 1. So we have successfully kind of figured out the coefficients of our blending function. So now we need to take those and put them back into the Bernstein polynomials. So here's the Bernstein polynomial. And so when we put the first one in, we have to remember what our n and I are. And so for our first Bernstein polynomial, B03, it's 3 choose 0 times U0, 1 minus U to the 3 minus 0, which is just, this first thing is 1, so it's 1 times 1 minus U to the cubed. The Bernstein polynomial 1 comma 3 has the 3 choose 1, U to the first, 1 minus U to the 3 minus 1, which is 3U, 1 minus U squared. And the same with the other two. Does anyone have any questions on where that came from? How we're getting that?
I have a question about the coefficient C. Does it always follow that polynomial triangle?
It always follows the polynomial, the Pascal's triangle.
Yeah.
It always follows that. So, yeah. So now what does the summation sign tell us? Well, it tells us to just add these things together. So we take point 0, multiply it times the first Bernstein polynomial, P1 times the second Bernstein polynomial, P2 times the third, and P3 times the last Bernstein polynomial. And that is the equation of this curve. Now, we probably should have a vector, a line, a bar over top of each of these points because it represents x, y, and z. Each of those points is a vector, okay? X, Y, Z. So let's look at our first, so go back. We're going to look at each of these blending functions. We're going to look at the blending function 1 minus u cubed, 3u, 1 minus u squared, 3u squared, 1 minus u, and u cubed. And so the first basis function, the first blending function is 1 minus u cubed, and the curve looks something like that. 3u, 1 minus u squared, the curve looks something like that. 3u squared, 1 minus u, it looks kind of skewed to the right. And u cubed is just this power curve running up to the right. What do those things do for us? Question?
Yeah, our u value just goes from 0 to 1, right?
The u is always 0 to 1.
Okay.
Starts at 0, ends at 1. Okay. So what do those things do? Well, those things tell us collectively how the curve moves as a weighting function applied to what? As a weighting function applied to each of the points. Okay? So if we stack these three curves on top of each other, okay, and we ask the question, so there's our curve, we ask the question, when u is 0, where does the curve begin? Well, it's this curve here is valued at 1, and it's multiplied times 0.0. And what happens to all of these other blending functions? They are 0. And so these other 3 points have how much effect on the starting position of the curve? 0. Okay? No effect whatsoever. If we move partway across, so we move a third of the way or something across, then we can look, and based on these values that we read off to the left, based on these values, those things get multiplied times the x of 0, times the x of 1, times the x of 2, times the x of 3, and that value is the new x value of the curve. It's also, you take these weights and multiply them times the y, the y, the y, the y, the y, and it tells you the y value a third of the way along the curve. Does that make sense? So if we keep working along on this thing, these are the values that get multiplied times our points, weighting. And notice as we move further and further down the curve, what effect is the first point having on the curve as we move further towards the end? It is having less and less and less effect to eventually we get to the end. U is now 1. The first point goes away. The second point goes away. The third point goes away. And the only thing that is in effect when U is 1 is the full value of x, y, and z of the last point. Okay? So these Bernstein polynomials are nothing more than weights that get multiplied times the point and get summed up to shape the curve along. So what's the x, y, z mapping functions of this look like? Well, for the x, it's just the x value of every point multiplied out and summed up. For the y, it's just the y value. For the z, it's just the z value all summed up. Okay. What if you wanted to represent that curve by a matrix? Why would you ever want to represent a curve by a matrix? It's much easier to program. That's how the graphics system is able to run things so fast, is it holds these things not in equations, it holds them in matrix form, and it holds them in a simplified matrix form, to where all it has to do is provide a u value, and everything else is a number. We'll see that in just a second. So going from our equation, from this equation, and I now have bars over the top of it, going from that equation to a matrix form, how is it done? Well, it's done pretty easily, but it may have been a day or two since you've done matrix math, so we're going to kind of step through this. We can pull out all of the p's out of this and put the p's in a column. When we do that, we're left with a row vector of the Bernstein polynomials. 1 minus u cubed, 3u, 1 minus u squared, 3u squared, 1 minus u, and u cubed. You multiply those two together, you get exactly the equation up above. Can we simplify the row vector? Can that be simplified? Sure, we can think about pulling the u out of this equation, out of this vector. We can separate the u's. So one way to do that is to kind of look at what's here. Excuse me. First thing we did is multiplied the p's out, or then multiply them, we separated them. So the first column is x's, the second column was y, the third column is z. Now what we want to do is we want to actually separate out the u out of this row vector. To do that, what we need to do is kind of expand these things. So the first 1 minus u cubed is 1 minus u, 3u, plus